So now that we talked about some of the common streams creation operations, let's talk about common aggregate operations. And we'll see that there's a couple of different types of aggregate operations, but in general, an aggregate operation is used to perform some behavior on the elements in a stream. That's its purpose in life. Behaviors are typically implemented by lambda expressions or method references that correspond to some functional interface. So that's what a behavior typically is. Here's an example. So you can see here that we have the map intermediate operation, and map takes a behavior which is a method reference that will capitalize each element in the stream in a consistent capitalization scheme. So that's how that works. Some aggregate operations perform their behaviors on all the elements in the stream. So they basically run to completion, unless an exception is thrown, but we'll pretend for the moment that that isn't going to happen. So many of them just run until they're done. A good example of that would be something like map or filter. Other aggregate operations only perform behaviors on some elements in the stream. In other words, they short circuit. So an example of that would be operations like limit, which only takes a certain number of elements, or take while or drop while. And we'll talk about all these other methods. You don't have to know what they are at this point. Just be aware that some things are short-circuiting, some things run until all the stream elements are processed in one way or another. The aggregate operations are commonly composed together to form a pipeline of processing phases. You're possibly familiar with the concept of water filtration systems. People often put them in their houses, especially if they live in an area that doesn't have very good water. And so you'll have a filtration system where there's a set of filters that the water flows through to remove impurities, and hopefully at the very end you get pure water coming out, which is nice. So that's the kind of idea. Think about that when you think of a pipeline. That's sort of the idea to think about here, is flowing through a series of transforming entities or processing steps. As you can see here in the streams world, the Java streams world, the output of one aggregate operation, like the output of the stream source, is then piped into or connected into the next one in the stream. So we just kind of flow through there. And if you think about this from a functional perspective, like a mathematical functional perspective, it's about composing functions. So we get the input x, and then this aggregate operation outputs f of x, where f is the behavior, and then that gets piped into this other aggregate operation with the behavior g, and the output there is the output of g of f of x, and so on and so forth. So this sort of sounds like your 8th grade math class or whatever. You're composing functions together. Java Streams supports pipelining these things using so-called fluent interfaces, or the fluent interface pattern. The fluent interface pattern is used in other contexts as well, not just in Java Streams. Typically, it's used when you want to chain together a bunch of method calls, and it usually works by having a method return an object or a reference to an object so that you can then call another method on the output of that. Very, very commonly used in a lot of web programming frameworks. In this particular case, we have our example of Hamlet character names we're going to do some transformation to, and we're going to chain them together through fluent interfaces by saying stream of .filter, .map, .sorted, .foreach. The of factor method, as we've talked about now a number of times, is used to create a stream from an array of elements. So we get a stream out of an array. We then connect that to filter, which gets rid of anything that doesn't start with an uppercase or lowercase h. We then go ahead and use the map intermediate operation to capitalize everything in a nice, consistent way. We then sort the final set of results, which will be things that are starting with h that are now capitalized consistently. And the final result here is the for each aggregate operation that does the action on each element of the stream. For each is kind of interesting because unlike almost everything else you see in the stream, this is actually going to have a parameter that expects to have a side effect. So the side effect in this case is printing the results to the standard output. Very few other aggregate operations in the streams framework have side effects or should have side effects. This is one that does. So it's kind of the exception that proves the rule, as they like to say. Now, another thing to note here, and we may or may not talk about this in more detail, so I'll talk about it now just so you have an awareness of it. If you want to learn more about this, take a look at this link. The way that this works under the hood is through something called internal iteration. And what you see is we're iterating through everything, but you don't actually see the iteration. There's no iterator. An iterator is another Java construct that's been around since the beginning of time, basically, and it implements the iterator pattern. But we don't use the external iteration mechanism that's baked into normal Java through the iterator interface. Instead, we use internal iteration. And there's two reasons that they use internal iteration. Number one, it allows transparent optimization. So if we want to change this code here, which is a sequential processing sequence, to a parallel processing sequence, we don't have to change anything other than to insert the .parallel intermediate operation between .of and .filter. Everything else stays exactly the same. Were we to use external iteration, it would be a nightmare trying to convert from sequential to parallel. So one reason is for transparent optimizations. There's other optimizations we can do as well. We won't talk about that till later. We talk about the internals of streams. And it also incurs fewer accidental complexities because we're not exposing the iterations. Of course, there's always, with everything, there's always trade-offs. Because we don't expose the iteration, stopping the stream in the middle takes more thought, and it typically requires throwing exceptions, but we'll come back to that later too. In contrast, the old-fashioned way of doing things, which involves iterating using loops and/or Java iterators, has a lot more complexities lurking in there. So you can see here, for example, that we've got explicit control constructs. We make ourselves a new list, new linked list. Then we use an index-based for loop. We have if-else statements in here. We have another for each loop at the bottom, and so on. And there are just more opportunities for things to go wrong, especially with things like index-based for loops. Index-based for loops are notoriously tricky because you have off-by-one errors and all these other problems, accidental complexities. So the other problem is it's very hard to optimize and parallelize this without a lot of extra surgery taking place. This is the same behavior that we see over here. It's just done in the more traditional object-oriented way. So that's the end of the discussion about common aggregate operations.